Welcome everyone, and welcome to the AluVET vocational training and education for the aluminium sector. This training is co-funded by the Erasmus programme of the European Union. I am Jan Lukaszewski, the Technical Manager of the Aluminium Federation in the United Kingdom. The Introduction to Metals series of modules explains the simple theory of metals and of metallurgy to enable students in subsequent modules to understand aluminium, its alloys, how it is heat treated, and how it is rolled, extruded, and/or welded. In this module, we shall learn about how metal grains are formed and their effect on the properties of metals. Then we shall have a basic introduction into how alloys work and the effect of alloying elements. This project is funded with the support of the European Union. This publication reflects only the views of myself and the Aluminium Federation, and the Commission cannot be held responsible for the use which may be made of the information contained therein. The aim of this module is to gain knowledge about how metals grow into grains and the effect of grain boundaries, how different metals form into alloys, to understand metal alloying and the nature of inclusions and the effect of inclusions. In rolling, extruding, or welding aluminium, this module will enable you to understand what the effect the processes have on the resultant structures, products, and strength of those structures to enable you to design in quality and ensure defect products. This module follows on the previous one, where we explored the solidification of metals. Now, as a molten metal cools, the atoms come together and they form a face-centered cube, in the case of aluminium. And a metallic bond starts to form across the atoms, forming the face-centered cube. In the area from freezing start temperature of an alloy to the freezing finish temperature, atoms come together and start to form single cubes throughout the liquid. And millions of these haphazardly distributed single cells are nucleated throughout the cooling liquid and form into face-centered cubes. So between the freezing start temperature and the freezing finish temperature of an alloy, millions and millions of face-centered cubes start to form. And these face-centered cubes are differently orientated. So they are completely different orientated throughout the freezing liquid. Different orientations, so they'll be corner to corner, face to face. Thousands and thousands of these face-center cubes are starting to solidify through the liquid, and they're randomly orientated, completely randomly orientated. Now, as cooling continues, so the temperature falls from the freezing start to the freezing finish temperature, the single cells progressively grow in the direction of the principal axis. That is the random orientation of the seed cell. So millions and millions of these face-centered cubes are now starting to grow, and they're going to be growing in random directions. Now, the 5 atoms of all 6 faces of each face-centered cube will become shared with and form adjacent cubes. And the growing and sharing of the 6 faces of the face-centered cubes will be replicated many thousands of times across the adjacent cubes, growing into lattices. So throughout the freezing start to the freezing finish temperature of an alloy, thousands and thousands of crystals will be growing randomly throughout the cooling liquid within the mushy area. Now, as all of the liquid is eventually solidified into crystals, there will be a mismatch. And because of the mismatch of the mismatch will be that of the original seeded cubes growing into crystals. And because there is a mismatch, the face-centered cubes grow randomly into crystals. The crystals are solidifying following the original orientation of face-centered cubes. As all of the liquid is solidified, the crystals come together, and they will come together at different angles, so corner to corner, face to face, complete mismatch between each other. And as they impinge against each other, they form boundaries. And because the crystals are impinging against each other in different angles, they cannot grow together into a single crystal. So consequently, the individual crystals now have clear boundaries of mismatch between them around each other. And these boundaries effectively form grains, the grains being the growing crystal within the boundary that impinges against the adjacent grains. The metallic bond cannot fully form between the adjacent grains because of the boundaries. There is a mismatch between the boundaries as the gaps are too great for the electron cloud to form against. So the crystals develop into individual grains surrounded by boundaries. And there are distinct boundaries between all of the adjacent grains. And boundaries are an area of mismatch across which the metallic bond cannot form. Now, on final solidification, so all of the liquid solidified at the freezing finish temperature of an alloy, we end up with a network of boundaries between and surrounding all of the grains. Thus, all of the grains are surrounded by a network of grain boundaries. And effectively, the grain boundaries mirrored the mismatch of the original solidifying face-centered cubes. Now, we have a problem that even under the most powerful microscopes, we cannot see atoms, nor can we see the face-centered cubes. All we can see under a microscope are the grain boundaries and the grains. And in the middle of the slide, you see a simplified grain boundary network. And on the right-hand side, the colored picture, you can actually see what grains look like under a microscope. And look at the grain boundaries. Now, grain boundaries are mismatched between adjacent grains, so they are physical barriers. And as the electron cloud cannot fully migrate across nor completely form the metallic bond between adjacent grain boundaries are therefore planes of weakness. So you can see in the picture, within the grains, the electron cloud can be shared by all the atoms, but only a few electrons can sort of pass through the grain boundaries. So the grain boundaries are much, much weaker than the grains themselves. So the grain boundaries are therefore planes of weakness, lines of weakness. The network of grain boundaries are a network of weakness. Now, being planes or lines of weakness, cracks will propagate through the grain boundaries. If you have fine grains, you have large grain boundary networks. So many, many grain boundaries through which the cracks have to meander. And each time a meandering crack hits a grain, it is disrupted. And each time a crack encounters a grain, it has to start a new crack. So large grains have minimal grain boundary contact areas between them, and they offer clear crack propagation cracks. Thus, fine grains and fine grain networks interrupt crack propagation and exhibit high strength. Large grain networks, so large grains have short short grain boundaries, so offer clear crack propagation. So fine grains have many, many long grain boundaries, so offer great resistance to cracks. So in the picture, if you look at the bottom, in the middle bottom, you can see a very large grain size. And you can see that effectively a crack would only need to propagate through 2 grains. In the top right-hand side, you can see a very, very fine grain network, and you see that a crack will have to propagate through probably upwards of 100 grains in that. So the yield strength and tensile strength increase with fine grain size. The finer the grain size, the stronger the structures, because cracks have great difficulty in propagating between fine grains. So the finer the grain size, the stronger the structure. The finer the grain size, the higher the yield and the tensile strength. The larger the grains, the lower the strength of a metal, the lower the yield and tensile strength. In the previous module, we very, very briefly mentioned solid solubility. In a solid state, there is limited solubility of solute atoms within the solvent metals. Remember, aluminium is the principal, the main metal that we're considered of. That is the solvent metal. Alloying elements that we will add to be the aluminium will be called the solute metals. And solute metals have only limited solubility within the aluminium. Go back to our beaker of water with sugar at the bottom. In the solid state, the alloying elements, the sugar at the bottom, has only limited solubility in aluminium in the water. Now, this means that in the solid state, aluminium can absorb into its crystals solute alloying aluminium. Now, solid solubility is where in the solid state, the solute atoms can migrate and be dissolved or absorbed into the crystal lattices of the solvent aluminium. What I'm trying to say is that in the solid state, aluminium, like a beaker of water, can absorb some sugar. Aluminium can absorb within its grains some of the solute alloying elements. Now, as we increase the temperature, so we warm up our beaker of water, the sugar dissolves. And in the same way, because the atoms, metal atoms expand with increase in temperature, so the solvent atoms, the aluminium, can absorb more solute, the alloying atoms, into the grains. So solid solubility is the ability of aluminium to absorb within its grains alloying elements increase with temperature, just like the sugar dissolving into warm water.